In this video, you're going to learn about radians, a way of measuring angles. We're going to build on your current understanding of angles at GCSE. I'd like you to start out by just studying this image. Look at it and see what you notice. Pause the video now and do that. Okay, to remind you of some vocabulary, we have an arc of a circle here in red and here in blue. The green bit is a sector of a circle, and the purple bit is, well, we don't really have a name for that. We could consider it as maybe one big sector, take away another sector. I'm going to get you doing some calculations now. I'm going to label that angle as 51 degrees, and I'd like you to try and remember how to do the length of an arc and the area of a sector from GCSE. Pause the video now and calculate the length of the red arc, the blue arc, this green sector and the purple area here. Do that now. Pause the video. Okay, 3, 2, 1, I'm coming in. I'll actually just give you some hints before going through all of the answers. Remember that the arc length we can consider as a fraction of the full circle, of the full circumference. So the circumference is 2 pi r, 2 times pi times the radius, and the fraction of the circle is the angle divided by 360 degrees. We can do similar for the area of a sector, the fraction times the area of a circle. So if you didn't manage to calculate them yet, pause the video again and use those formulas, use that understanding now. Okay, here come the answers. I'm going to give them all to 2 decimal places. The arc length, the red arc length was 1.78. The blue arc length was 11.26. The green area was 7.12 and the purple area was 7.07. Note how I've not put units on any of these because the lengths on the axis didn't have units. If you'd use centimetres, if you considered these as centimetres, then the arc lengths would be in centimetres and the areas would be in centimetres squared. Well done if you got those 4 values. Here is neatly those 2 formulas that we used. You might want to copy them down in your notes. All right, I'm going to ask you a question now that you might not have considered before. Why are there 360 degrees in a full turn? You were told this at primary school, probably, that there are 360 degrees in a full turn, but maybe you never questioned it. Why 360 and not 300 or 100? Or just 1, and we work in fractions? The origin of this is not exactly known. It was perhaps come up with first by Babylonian mathematicians. Babylonia was an ancient civilization roughly where Syria and Iraq are now. Maybe it was them, maybe it was our friends the ancient Greeks, maybe it was ancient Indian mathematicians. There's evidence that each of these civilizations used it. Maybe they came up with it independently, maybe one of them came up with it first. Why 360? Probably just because there are loads of factors of 360. So if you consider splitting up a full circle into different fractions, having loads of factors is quite useful. Say I wanted 1/5 of a circle, then that would be 72 degrees, a nice integer. And splitting up this circle into different fractions gives a lot of integers because of all the fractions, of all the factors. But what if you used a different measure? What if something was more useful? My mate Chad here is an American and he's quite confident, and being an American, he likes the metric system. So metres, kilometres, whatever, instead of miles and yards. And he likes it because the metric system is based on powers of 10. So he's going to say, Chad is going to say, what if there were 100 units in a full turn? And because he's so confident, he's going to call them chads. There are 100 chads in a full turn. So he has set up this new challenge for you. If there are 100 chads in a full turn, and this angle here is 20 chads, can you figure out these lengths and these areas again? Consider again the fraction of a full circle that each of those bits fills up. Pause the video now and try to get your head around that. All right, some hints again first. So this here, the red bit is 20/100ths of the full circle. Maybe you figured that out. The blue bit here, we need to do some subtraction. If there are 100 chads all the way round, then there will be 50 chads in a half turn and 25 chads in a right angle. And you can use that to figure that angle there. If you haven't got it all, again, pause the video now. All right, we've got some answers coming up. The formula for the circumference of a circle is exactly the same. It's always 2 pi r, and the area is always pi r squared. So this bit here is 20/100 times 2 times pi times the radius, and it turns out to be, to 2 decimal places, 2.51. The blue one is at an angle of 30 chads, and that one turns out to be 9.42. The green is 10.05, using the area of a circle instead, and the purple one is 7.07 at an angle of 25 chads. You might have noticed that that's the same area as before. And maybe you've had a think about why that might be the case. Why is that one exactly the same area as when we use degrees? Have a think about that for yourself. All right. So the formulas in chads become these. If we've got 100 chads in a full turn, then we've got this fraction times the circumference, or this fraction times the area. Now that's maybe quite nice using metric, because there are 25 in a right angle and 50 in a half turn. But is there a better measure? Could we put something different on the bottom here to make this easier, to simplify it a little bit? That's what radians do. If we measure this in radians, then we say that there are 2 pi radians in a full turn. Now just think about that for a second. 2 pi, 2 times pi, pi is 3.14, so 2 lots of pi is about 6.28. But it doesn't end there. That is a decimal that never recurs. It just goes on all the way, all the way, all the way, that way. To think of there not being a whole number of radians in a full turn. In a full turn, there are about 6.28. Now that's a bit weird, since we're used to there being a whole number of degrees in a full turn. But let's see how that works out. That becomes 2 pi there, and the 2 pi's cancel out. So the arc length just becomes the angle times by the radius. How weird is that? So a quick example of that. If the radius here was 5 and the angle was 2 radians, what's the arc length? We'll just use this formula and we get 2 times 5 is 10. And the arc length now becomes a nice, neat whole number. How nice is that? Let's just figure out this formula for the area of a sector as well. So that becomes 2 pi we're measuring in radians now, and this simplifies to half times theta times r squared. Not quite as nice maybe because we've still got half there, but still the formulas don't have pi in them anymore. There they are neatly, in case you want to copy them down for your notes. And you might have guessed what's coming up. I've got this new problem for you now. I've labelled this angle as 1 radian, and I'd like you to figure out the same lengths and areas. You might want to use this. You might want to do this using the simplified formulas that we just came up with, or you might want to still treat this as a fraction of a full circle. So this was a fraction of a full circle times 2 pi r. You can do that either way. Try to figure out the lengths and areas as you did before. Pause the video now and try that. Okay, coming up, answers. I'm going to use this one. So the arc length here is just 1 times 2. That arc length there is 2. Okay, just dwell on that. With a radian of 1 radian, an angle of 1 radian, this arc length here is the same as this length here. How beautiful is that? I'm going to go to the green area next. Well, in a similar way, just plug it into the formula, you get that the green area is just 8. Exactly 8. It's a half times 1 times the radius squared. Lovely. The other two are slightly trickier because pi comes in. That angle there becomes pi take away 1. And so this length here becomes the radius times the angle. That is about 10.7 to 1 decimal place this time. And the purple area here, well, that quarter turn will be a half pi. And if you work out the purple area using that, you should have gotten, 7.07 again. Why does that make sense that that purple area was the same every single time? It's because that purple area never depended on this changing angle. It was always just a quarter of a circle. No matter what unit we use, this was a quarter of a circle, and so the area stayed the same. Well done if you got those answers there. A quick note on the size of these radians. This angle here is 1 radian, and this angle here is pi radians, so about 3.14. It's a common mistake to treat pi as 1. People think of pi as like a unit, and you say 1 pi radian, so that's like 1. No, pi is about 3.14, so there are about 3.14 radians in a half turn. And 1 radian looks like this. It's about 57.3 degrees. We're going to do a little practice now on converting between the two, radians and degrees. I've given you at the top here what you should remember and base a lot of these calculations on. So 2 pi, that was how we defined it in the first place, was 360 degrees. But can you use this ratio at the top and convert it into each of the others? Have a go yourself first. Okay, I'll give you the first one of this one and the first one down here. So to get to this one here, we just divide both sides by 2 and we get 90 degrees. A right angle is a half pi. We often pronounce that as pi by 2, as a shortening of pi divided by 2. To get down here, well, what do we do to 180 to get to 30? we divide it by 6. So do that to the other side and you get pi by 6. If you haven't got the others yet, pause the video again and do those now. Alright, I'm just going to fill in some answers. Pi by 3 turns out to be 60 degrees. 2 pi by 3 is 2 lots of that. 120 degrees. 5 pi by 12. If you do 180 divided by 12, you get... Maybe I should have prepped that. I'm just using my calculator. You get 15. 15 times 5 is 75 degrees. And 3/5 is going to be 36 times 3, which is 108 degrees. Best way I think of getting to 150 is doing 5 lots of this one. So that will be 5/6 pi or 5 pi by 6. Down here, what's the best way of getting 144 degrees? I think the best way is to consider just some fractions. How do we turn 180 into 144? We times by this fraction. Simplify that fraction, 144 over 180, and you get 4/5. So this is 4/5 pi. And this one's a bit weirder. 7 radians. How do we turn the number pi into the number 7? Well, we'd have to times by 7 and divide by pi. Do that to the right-hand side of the ratio again, and you do divide by pi. You get about 401 degrees. Have a think about why that makes sense, that is a bit more than a full turn. Lovely. That's all the calculations I'm going to get you to do. Maybe, if you're not quite confident enough with these, you can make up some of your own. They're very easy to make up. Just pick a fraction and think, well, how many degrees is that? And maybe you can check it on your calculator or figure out some way of drawing it. Radians will become even more useful later on in the A-level course when we consider graphs of sine and cos and tan and other trig functions. The graphs actually become a lot nicer when we're using radians as well. And there are different ways that we use radians, and the stuff that you've been doing in trigonometry so far also just makes sense. I'm going to leave you in this video now with this animation just for you to watch and maybe figure out what's going on. Okay, that's quite enough of that.